Article 230.71 of the National Electrical Code addresses the size of overcurrent protective devices. Specifically, it states that the size of the overcurrent protective device for conductors supplying a single-phase appliance or a single-phase tap shall not exceed the rating of the branch circuit conductors. In the scenario described, where a 200 amp service using 4/0 aluminum conductors feeds 3 meter bases, each supplying a fuse box with 2/2/4 aluminum conductors, replacing the fuse panels with 3 100 amp main breaker panels creates a violation. The critical point is that the 4/0 aluminum service conductors are rated for 200 amps, while the 2/2/4 aluminum feeders from the meters to the panels are rated for 100 amps. Installing 3 100 amp main breaker panels means connecting 300 amps of panel capacity to a 200 amp service. This violates the National Electrical Code rule because the overcurrent protective devices, the main breakers, exceed the rating of the service conductors. To clarify the concept of ampacity and overcurrent protection, consider the following. Ampacity refers to the current carrying capacity of a conductor, which is the maximum amount of current a conductor can carry continuously without exceeding its temperature rating. Overcurrent protection is the use of devices like fuses or circuit breakers to protect conductors and equipment from excessive current, which could cause overheating, fire, or damage. The National Electrical Code sets standards for the safe installation of electrical wiring and equipment, including requirements for conductor ampacity and overcurrent protection. When determining the appropriate size of overcurrent protection, the National Electrical Code mandates that the overcurrent device should protect the conductor from overload. This means that the overcurrent device rating should not exceed the conductor's ampacity. In the given scenario, the service conductors have a certain ampacity, and the feeder conductors have a lower ampacity. The main breakers installed in the panel should not allow more current to flow than the feeder conductors can safely handle. Installing 3 100 amp main breaker panels means the system could potentially draw 300 amps, exceeding the 200 amp capacity of the service conductors and the 100 amp capacity of each set of feeder conductors. This is a violation of the National Electrical Code. To comply with the National Electrical Code, the main breakers installed must not exceed the rating of the service conductors. A solution would be to install 380 amp main breaker panels. This would provide a total panel capacity of 240 amps, which is still above the 200 amp service capacity, but each individual feeder is protected at 80 amps, which is below the 100 amp rating of the 2/2/4 aluminum conductors. A more conservative, and often preferred, approach is to ensure the sum of the main breaker ratings does not exceed the service conductor ampacity. Here's a breakdown of why this is so important. Firstly, safety. Overcurrent protection is essential for preventing electrical fires and protecting equipment from damage. If the overcurrent protection is not properly sized, it may not trip in the event of an overload or short circuit, leading to dangerous conditions. Secondly, code compliance. The National Electrical Code is designed to ensure electrical safety and proper installation practices. Violating the National Electrical Code can result in fines, legal issues, and potential liability in the event of an accident. Thirdly, system integrity. Proper overcurrent protection helps maintain the integrity of the electrical system by preventing damage to conductors, equipment, and appliances. This ensures reliable operation and minimizes the risk of downtime. In this specific situation, replacing the fuse panels with breaker panels is a common upgrade, but it must be done in accordance with the National Electrical Code. It's essential to carefully evaluate the load calculations, conductor ampacities, and overcurrent protection requirements to ensure a safe and compliant installation. When dealing with electrical installations, it's always recommended to consult with a qualified electrician or electrical engineer who can perform the necessary calculations and ensure that the installation meets all applicable codes and standards. Considering other factors that influence conductor ampacity and overcurrent protection is critical for safe and code-compliant electrical installations. These factors include ambient temperature, conductor bundling, and the type of terminations used. Firstly, ambient temperature. The ampacity of a conductor is affected by the ambient temperature in which it is installed. The National Electrical Code provides correction factors to adjust the ampacity based on ambient temperature. If the ambient temperature is higher than the standard rating, the ampacity of the conductor must be reduced to prevent overheating. Secondly, conductor bundling. When multiple conductors are bundled together, they can generate more heat than if they were installed separately. The National Electrical Code requires that the ampacity of bundled conductors be derated to account for this increased heat. Thirdly, termination temperature rating. Electrical equipment, such as circuit breakers and powels, have a temperature rating for the terminations. The conductors connected to these terminations must have an ampacity that is suitable for the termination temperature rating. Using conductors with insufficient ampacity can lead to overheating and failure of the terminations. Therefore, when selecting conductors and overcurrent protection, it is crucial to consider these factors and apply the appropriate correction and derating factors as specified in the National Electrical Code. This will ensure that the electrical system is safe and reliable. Considering voltage drop is another crucial aspect of electrical installations. Voltage drop refers to the reduction in voltage that occurs along a conductor due to its impedance and the current flowing through it. Excessive voltage drop can cause equipment to malfunction, reduce the efficiency of lighting, and even damage electrical components. The National Electrical Code recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders. To minimize voltage drop, larger conductors can be used, or the length of the conductors can be reduced. Voltage drop calculation should be performed during the design phase to ensure that the voltage at the equipment terminals is within acceptable limits. In addition to conductor ampacity, overcurrent protection, and voltage drop, grounding and bonding are essential for electrical safety. Grounding provides a path for fault current to flow back to the source, allowing the overcurrent protection device to trip and energize the circuit. Bonding ensures that all metal parts of the electrical system are electrically connected, minimizing the risk of electric shock. The National Electrical Code specifies requirements for grounding and bonding to ensure that the electrical system is safe and effective. Grounding electrode systems, equipment grounding conductors, and bonding jumpers are all critical components of a properly grounded and bonded electrical system. Regular inspection and testing of the grounding and bonding system are essential to ensure its continued effectiveness. Surge protection is also an important consideration, especially in areas prone to lightning strikes or power surges. Surge protective devices, or SPDs, are designed to protect electrical equipment from transient voltage surges, which can damage or destroy sensitive electronic components. SPD should be installed at the service entrance and at downstream panels to provide comprehensive surge protection. The selection and installation of SPD should be based on the specific needs of the application and in accordance with the National Electrical Code. Arc fault circuit interrupters, or SIs, are another important safety device that can help prevent electrical fires. SIs are designed to detect arc faults, which are dangerous electrical conditions that can cause fires. SIs strip the circuit breaker when an arc fault is detected, preventing the arc from igniting nearby materials. The National Electrical Code requires SIs in many locations, including bedrooms, living rooms, and dining rooms. Regular testing of SIs is essential to ensure that they are functioning properly. Ground fault circuit interrupters, or GFCIs, are designed to protect people from electric shock. GFCIs trip the circuit breaker when a ground fault is detected, preventing electricity from flowing through a person's body. The National Electrical Code requires GFCIs in many locations, including bathrooms, kitchens, and outdoor areas. Regular testing of GFCIs is essential to ensure that they are functioning properly. In summary, electrical installations must comply with the National Electrical Code to ensure safety and reliability. Conductor ampacity, overcurrent protection, voltage drop, grounding and bonding, surge protection, SIs, and GFCIs are all important considerations that must be addressed during the design and installation process. Consulting with a qualified electrician or electrical engineer is essential to ensure that the electrical system meets all applicable codes and standards. When upgrading electrical systems, such as replacing fuse panels with breaker panels, it is crucial to perform a thorough load calculation to determine the actual electrical demand of the building. A load calculation takes into account all of the electrical loads in the building, including lighting, appliances, and equipment. The load calculation is used to determine the appropriate size of the service entrance, feeders, and branch circuits. The National Electrical Code provides detailed instructions for performing load calculations. Using an accurate load calculation ensures that the electrical system is properly sized to meet the building's electrical demand. Proper labeling of electrical panels is essential for safety and troubleshooting. The National Electrical Code requires that electrical panels be clearly labeled with the circuit numbers, the load served by each circuit, and the voltage and amperage ratings of the panel. Proper labeling makes it easier to identify and to energize circuits for maintenance or repairs. It also helps prevent overloading of circuits, which can cause overheating and fires. Regular inspection and maintenance of electrical systems are essential for preventing electrical hazards. Electrical systems should be inspected periodically by a qualified electrician to identify any potential problems such as loose connections, damaged wiring, or overloaded circuits. Maintenance tasks such as tightening connections and replacing worn components should be performed as needed to keep the electrical system in good working order. Safety training is crucial for anyone who works on or around electrical equipment. Electrical workers should be trained in safe work practices, including lockout-tagout procedures, proper use of personal protective equipment, and emergency response procedures. Ongoing training is essential to keep electrical workers up to date on the latest codes, standards, and safety practices. Lockout-tagout procedures are used to prevent accidental energization of electrical equipment during maintenance or repairs. Lockout-tagout involves disconnecting the power source and attaching a lock and tag to the disconnect switch to prevent it from being turned on. Only the person who placed the lock and tag should remove it. Proper lockout-tagout procedures are essential for preventing electrical shock and other injuries. Personal protective equipment, or PPE, is used to protect electrical workers from electrical hazards. PPE includes items such as rubber gloves, safety glasses, and arc-rated clothing. The type of PPE required depends on the specific task and the potential hazards involved. It is important to use the correct PPE and to inspect it regularly for damage. Emergency response procedures should be in place in case of an electrical accident. These procedures should include instructions for de-energizing the circuit, providing first aid, and calling for emergency assistance. Electrical workers should be trained in emergency response procedures and should know how to respond quickly and effectively in the event of an accident. When working on electrical systems, it is important to use the correct tools and equipment. Electrical tools should be insulated and in good working order. Using the wrong tools or equipment can increase the risk of electrical shock or other injuries. It is also important to follow the manufacturer's instructions when using electrical tools and equipment. Electrical safety is everyone's responsibility. By following safe work practices and taking precautions to prevent electrical hazards, we can all help to create a safer work environment. Reporting any potential electrical hazards is also important so that they can be addressed before they cause an accident. In summary, upgrading electrical systems requires careful planning, thorough load calculations, and compliance with the National Electrical Code. Proper labeling, regular inspection and maintenance, safety training, lockout-tagout procedures, personal protective equipment, emergency response procedures, and the use of correct tools and equipment are all essential for electrical safety. By following these guidelines, we can ensure that electrical systems are safe and reliable. When evaluating an existing electrical installation for an upgrade, it is essential to consider the age and condition of the existing equipment. Older equipment may be outdated or may have deteriorated over time, which can increase the risk of electrical hazards. Replacing old or damaged equipment with new, code-compliant equipment can improve safety and reliability. It is also important to check the wiring for any signs of damage or deterioration. Damaged wiring should be replaced to prevent electrical shorts and fires. In some cases, it may be necessary to upgrade the entire electrical system to meet the current electrical demand of the building. This may involve replacing the service entrance, feeders, and branch circuits with larger conductors and higher rated equipment. Upgrading the electrical system can improve the safety and reliability of the building and can also increase its value. When planning an electrical upgrade, it is important to obtain the necessary permits from the local building department. Permits ensure that the work is performed in accordance with the National Electrical Code and other applicable regulations. The building department may also require inspections to ensure that the work is done properly. Working without permits can result in fines and delays. It is also important to hire a qualified electrician to perform the electrical upgrade. A qualified electrician has the knowledge, skills, and experience to perform the work safely and correctly. A qualified electrician will also be familiar with the National Electrical Code and other applicable regulations. Hiring a qualified electrician can help ensure that the electrical upgrade is done right the first time. After the electrical upgrade is complete, it is important to test the system to ensure that it is working properly. This may involve testing the voltage, current, and grounding to ensure that they are within acceptable limits. Testing can help identify any potential problems before they cause an accident. It is also important to provide the building owner with documentation of the electrical upgrade, including the permit, the electrician's contact information, and the results of the testing. This documentation can be helpful for future maintenance and repairs. In conclusion, upgrading an electrical system is a complex process that requires careful planning, attention to detail, and compliance with the National Electrical Code. By following these guidelines, you can ensure that the electrical upgrade is done safely and correctly.